We want to talk about derivatives now graphically, so we're going to look at some graphs. Last time we looked at some tables and saw what happened when we zoomed in and looked at the rate of change and all that. So now we're going to start out very similar. We're going to start talking about a line and just notice some properties about it here. Okay, the slope of this thing is 2 because mx plus b, y'all remember that, so slope is 2. And all that means is if you take any 2 points and you find the change in x, in this case is 1, and the change in y, which is 2, and you make the ratio of how much y changed divided by how much x changed, you should always get 2 back. So here you see 2 divided by 1, which is change in y over change in x, is 2. Okay, there's no units on this, so we can make up a word problem where something's changed to get 2 whatever per minute, but whatever. Just let's think about this just in terms of this graph. If we took the point here, 1, 2, and went over to the point 4, 8, well, now I'm moving from 1 to 4. Well, now that change is 3, and I'm going from 2 up to 8. Well, that's 6. Well, change in y is 6, change in x is 3, so it's still 6 over 3, which is still 2. Doesn't matter what 2 points you pick. Do the same thing down here. You do this. Now we're going from negative 3 all the way over to 4. Well, that's 7. And we're going from negative 6 all the way up to 8. Well, that's 14. Still 2. Constant rate of change. And if we zoomed in on this graph, it would look the same the entire time. The slope would look the same at least. So we could zoom in, zoom in, zoom in, zoom in. And no matter what 2 points we picked, still get this change of 2. Now, not all functions behave like that, but we can use this basic idea here and zoom in on a function and kind of see what happens. So let's take a look at x squared, pretty basic graph. And just to show you that it's not, you can't do the same thing as a line. For instance, if you find change in x over change in y here, or change in y over change in x is changing by 1, y is changing by 3. Right? We're going over 1 up 3. So there, for that interval, change in y over change in x, that's 3. But if we went from 1 all the way over to 4 and went up, now my change in x is 3. 1 to 4 is 3. But my change in y is 15. I went up 1 to 16. So now, change in y over change in x is 15 over 3, which is 5. So that's different, clearly. And because of that, we can't just call it change in y over change in x anymore. We've got to specify what interval we're looking at the changes. So this would be the change from 1 to 2, and this would be the change from 1 to 4. What did I just do there? 4, yeah, okay. So 4. Whew. And if you remember back from the numerical approach what we talked about, when you do that, what you're really finding there is the average rate of change of y, okay, our dependent variable, on that interval. So this is the average rate of change of y from 1 to 4. It's 5. And what that's really finding here is we're still finding a slope. We're finding change in y over change in x, but it's not the slope of this function. It's the slope of the line connecting these 2 points. This function is not a line, so this is not the slope of the function. If we connected this point to this point right here, like that, okay? That makes a line, you can see that, and the slope of that line is 3. But it's not the slope of the function. If we connected the points, this point to this point up here, well now it's much steeper. You can see this, and I missed it a little bit, but there you go. Now that has a slope of 5. Okay, so it's steeper, clearly, change of 5. But what happens is this is not a line, so like the line doesn't look like the function at all. But if we zoom in far enough, let's take a peek at this guy. If we zoom in around x equals 2, which is what I did here, for x squared, this thing starts to look like a straight line. It's still got a little bit of a curve here, but it starts to look like a straight line. We could zoom in even further and it will look even more like a straight line. But since it starts to look like a straight line in here eventually, then I should be able to find the slope between 2 points around x equals 2. And as I bring those points closer together on this graph, they start to look more and more like a line. So the slope around 2 should start to approach some number. So let's go back here. This case, this looks all weird. Let's kind of erase all this, and we'll talk about this on a big scale, and then we'll kind of zoom in some. So macro, then micro. So we're interested around 2. That's right here, okay? If we go from 2 to this point up here, so let's connect those points. You got this thing going on right there. Okay? That is not the slope of the function. It's a slope from this point here, 2, 4 to 3, 9. Okay, but it's an approximation to the slope at 2. If I want to make it a better approximation, I would move this point. I chose x equals 3. I would move it closer. I'd choose like x equals 2.1. And you'd see that the slope would be a little bit less, like that, if we brought those points close together. Okay, now that line that I'm drawing there, what I'm approximating as I bring the points close together, that's called a tangent line. And we're actually going to find the tangent line at this point here in a second. But main idea is, if you zoom in on some functions, okay, most functions that you're going to look at this year, not all functions, but most functions, they start to look like lines. And if they start to look like lines, you should be able to talk about the slope at a point. Since it starts to look like a line, we should be able to find some kind of slope on a small enough window. And that whole zooming in process, again, that we're doing here is really the limit process. We're zooming in further and further and further and further to see what happens here. So let's take a look at some point. Here's 2, right? I'm going to take this point here. So 2 we know is at 2, 4. I'm going to take the point 2.1, and when you square 2.1, make sure we're all on the same page here. When you square 2.1, 2.1 squared, you get 4.41. Okay, no problem. So this is 4.41. So if I connect these 2 points, that's going to create this line. All right. Now, if I try to draw it by hand here, it's going to look just like the function, because the function starts to look like a line. But you got to remember, no matter how far you zoom in, the function's not really a line. It's still a curve. It's just, the further you zoom in, it's harder to distinguish that curve. So even though I can connect these 2 points with a line, and it looks like the function looks like a line right there, it's not a line. So the slope that I'm finding here is not really the slope of the function. It's an approximate value, and you can see the further we zoom in, the closer our approximation is going to be. So let's calculate the slope here. The change in y over change in x, which is, again, this is what we're calculating, the average rate of change of x squared on the interval 2 to 2.1. That's what we're really calculating here. We get 4.41 minus 4, which is 0.41, divided by 2.1 minus 2. That's 0.1. Well, that gives me back 4.1. And if we started choosing points closer and closer and closer to 2, okay, just zoomed in further and further and further, we would find out that this average rate of change gets closer and closer and closer to 4. So that's what we call the slope of the function at 2. We call it 4. Now, it's a coincidence that the y value is 4 there too, but this is not the same thing as the y value. This is what we'd really be doing here to find this. We'd be taking the limit as x approaches 2 of y of x, okay, I'm using function notation here, y of x minus y of 2, which was 4, over x minus 2. And remember, y of x was really x squared, so we can plug him in there. This is what we're really doing here. We're taking this limit, which is the limit of the average rate of change, the change in y over the change in x. This is the change in y. X squared, for any x value I pick, will give me back a y value, and I'm finding out how much it changed from 4 while I was subtracting. Okay? So this thing is approaching 4. So the slope of our function, we're saying, is 4. So check this out. If I created a line that had a slope of 4 and went through this point 2, 4, it should look very much like this function. And actually, there it is. You can see this. This is my line. It has a slope of 4, and it goes through that point 2, 4. All right. And if I zoom in on that same window with that line drawn, my rectangle's off a little bit here for some reason. That's a little better. You can see the line close to 2, which is this point right here. This point here is 2, 4. Close to 2, this line's really indistinguishable from this function. All right. Now, we can find the equation of this line. Like I just said, it looks like this function has a slope of 4 around there. Right? We zoom in on it. Okay, we got 4.1 when we did this average rate of change on this interval. And I'm telling you, if you zoomed in further and further and further and further, you'd find the average rate of change was approaching 4 as your second x value approached 2. So our line has a slope of 2. The line that we're interested in here has a slope of 2, and it has to go through the point 2, 4. Well, if you find the equation of that line, you get, oh my god, I'm probably thinking I'm crazy. It has a slope of 4 and has to go through the point 2, 4. Well, that line is just 4x minus 4? Yeah, 4. There we go. This line has a special name. This is called the tangent line. To the function, which is x squared, at x equals 2. And all of the characteristics is that it has the slope of x squared, at x equals 2 and it has the y value of x squared at x equals 2. And again, if you look at the picture, we zoomed in. So here's what we're saying. We're saying that x squared is approximately equal to 4x minus 4 for x values close to 2. So what it does is it gives us a way to approximate x squared with a linear function. Now that doesn't seem super crazy at this point, because I mean x squared is not that difficult to deal with. It's a little bit easier. Like let's say I want to know what's 2.001 squared. All right, that might take a little bit of work to do that, but I know it has to be about 4 times 2.001 minus 4. Well, 4 times 2.001 is 8.004, and minus 4 is 4.004. So it's approximately this number. Okay, so our tangent line is really just used to approximate more difficult functions with lines. But the main idea here, again, for the graphical approach to derivatives is that if you take a function and you zoom in far enough, sometimes it starts to look like a line. And if it does start to look like a line, we should be able to find the slope of the line that it looks like. And to do that, you pick points closer and closer and closer together, and you can see you get this line here that's super close to the function at that point, and we call that the derivative. The slope of the function at 2 is 4. That is the same thing as me saying f prime of 2 is 4. We didn't call it f, we called it y. We'll call it y prime at 2 was 4.